That sound you just heard? That's a black hole feeding on a star. Not a Hollywood sound effect. Not a simulation made for a sci-fi movie. That is real astronomical data, converted into sound your ears can understand. But wait, black holes are silent, right? Space is a vacuum. Sound needs air. So how did scientists at Massachusetts Institute of Technology actually record a black hole eating? By the end of this video you'll understand how astronomers turned light into sound, what those eerie tones actually represent, and why this method is changing how we study the most extreme objects in the universe. Let's break it down. What actually happens when a black hole feeds? First, you need to understand what's happening physically. There are tens of millions of black holes in our galaxy, the Milky Way, alone. Most of them are quiet, invisible. They don't emit light. They just sit there warping space with gravity. But sometimes a black hole has a nearby companion star. And that's when things get violent. Imagine a normal star orbiting a black hole. The star is just doing its thing, burning hydrogen, shining peacefully. But the black hole's gravity is incredibly strong. It begins pulling gas off the star's surface. At first slowly, then faster. The stolen gas doesn't fall straight in. Instead, it spirals inward, forming a flat, spinning structure called an accretion disk. Think of it like a cosmic whirlpool made of plasma. Now here's the wild part. As gas in the disk rubs together, friction heats it to millions of degrees. Hot enough to glow in X-rays, the highest energy form of light we can detect. That's how we see black holes. Not the black hole itself, because light can't escape the event horizon. We see the chaos around it. The corona, the hidden engine above the disk. But the accretion disk isn't the whole story. Above the disk floats something even stranger. A region of extremely hot plasma called the corona. This isn't the same as the sun's corona, though it's similar in concept. This one can reach billions of degrees. The corona blasts out intense X-rays in all directions. Some of those X-rays travel straight toward Earth. Others bounce off the accretion disk. And that bounce is everything. Light echoes, cosmic echolocation. When X-rays bounce off the disk and return, they arrive slightly later than the direct X-rays. That tiny delay, often just milliseconds, is called a light echo. It works just like echolocation. Bats send out sound waves and listen for echoes to map caves. Astronomers send out X-ray bursts and measure how long the echo takes to return. By calculating the delay, scientists can measure the distance between the corona and disk, the size of the emitting region, the geometry of matter near the black hole. This method is called X-ray reverberation mapping. It allows scientists to study regions only a few dozen miles across, from thousands of light years away. That's like detecting the thickness of a coin on the moon. The breakthrough. Professor Aaron Kara at MIT has been leading this research. Using data from NASA's NICER telescope, mounted on the International Space Station, her team searched for echo signals. NICER stands for Neutron Star Interior Composition Explorer. It observes X-ray sources as the space station orbits Earth every 90 minutes. The MIT team built an automated algorithm called the reverberation machine. It scanned huge amounts of data looking for tiny echo delays. And they found something surprising. Echoes weren't rare. They discovered multiple stellar mass black holes, between 5 and 15 times the mass of our Sun, producing clear X-ray reverberations. That means this process is common. Black holes don't just quietly consume matter. They flicker. They pulse. They echo. What the echoes revealed. One black hole system, MAXI J 1820+070, gave scientists an even bigger surprise. Over several weeks, the echo delays got shorter. That meant the corona was shrinking. It collapsed from roughly 100 miles across to about 10 miles across. Imagine Manhattan shrinking down to the size of Central Park, but made of billion-degree plasma. Even more interesting, the corona appeared stretched vertically, like a glowing pillar rising above the disk. That structure may connect to powerful jets, beams of particles that shoot out near the speed of light. Those jets can influence entire galaxies, turning light into sound. Now let's answer the big question. How do you hear a black hole? You don't record sound in space. You convert data into sound. This process is called sonification. The MIT team worked with scientists and musicians to translate X-ray data into audio. Here's how they did it. X-ray frequency mapped to pitch. Intensity mapped to volume. Time delays mapped to rhythm. So when you hear rising and falling tones, you're hearing changes in X-ray energy. When you hear repeating pulses, you're hearing echoes bouncing between corona and disk. It's not fake. It's physics, translated into a different language. Why sonification matters. This isn't just for cool YouTube videos. The human ear is extremely good at detecting patterns. Sometimes scientists can hear irregularities or rhythms that are harder to spot visually in graphs. Sonification becomes another scientific tool. Another way to analyze data. Another sense added to astronomy. Why this changes black hole research. Here's the bigger picture. Supermassive black holes, the ones at galaxy centers, evolve over millions or billions of years. We can't watch them change in real time. But stellar mass black holes change in weeks or months. They are like scaled-down laboratories. By studying them we learn how matter behaves in extreme gravity, how jets form, how black holes grow, how they affect their surroundings, and ultimately, how galaxies evolve. The physics underneath it all. At the heart of this is Einstein's general relativity. Black holes warp space and time. Near the event horizon, time slows down. Light bends. Energy shifts. The X-rays bouncing around are influenced by curved spacetime itself. When we measure those echoes, we are measuring the structure of warped spacetime. In a way, we are listening to gravity. Final takeaways. Here's what we learned. Black holes aren't always invisible. When they feed, they glow in X-rays. X-ray echoes allow scientists to map regions near the event horizon. MIT's reverberation machine discovered multiple new echoing systems. Sonification lets us hear patterns in extreme gravity. Stellar mass black holes act as small-scale models for supermassive ones. Space may be silent, but with the right tools, we can still listen. Space may be silent, but with the right tools, we can still listen. And what we're really listening to isn't sound in the normal sense. We're listening to timing. We're listening to energy. We're listening to matter falling into one of the most extreme environments the universe can create. Let's zoom in even closer. Near a black hole, gravity is so strong that space itself is curved. Not metaphorically, physically curved. If you could see spacetime, it would look like a stretched rubber sheet with a deep well in the center. Anything that gets too close rolls inward. But as gas spirals toward the event horizon, something important happens. It doesn't just fall quietly. It accelerates. And when matter accelerates in extreme gravity, it releases enormous amounts of energy. In fact, black holes can convert matter into energy more efficiently than nuclear fusion inside stars. That means a feeding black hole can briefly outshine everything around it. And those X-rays we detect? They're coming from matter just milliseconds away from disappearing forever. The time delays in the light echoes are tiny, sometimes just a few thousandths of a second. But those tiny differences carry massive information. If the echo delay shortens, it means the corona is moving closer to the disk. If the delay grows, the structure is expanding. If the energy shifts toward higher frequencies, the plasma is heating up. These are not random changes. They are clues. Clues about magnetic fields twisting near the event horizon. Clues about how jets are launched. Clues about how black holes switch between states. Astronomers classify feeding black holes into different modes, often called hard and soft states. In the hard state, high-energy X-rays dominate. The corona is powerful. Jets are more likely to form. In the soft state, lower-energy emissions from the disk dominate. The system becomes more stable. What's fascinating is that black holes can flip between these states over weeks or months. And every transition leaves a signature in the echoes. That's why reverberation mapping is so powerful. We cannot directly see the event horizon of most black holes. They are too small and too far away. Even the famous image of a black hole's shadow required a planet-sized telescope network. But with timing alone, just measuring delays in light, we can reconstruct structures only a few gravitational radii across. A gravitational radius is basically the scale set by Einstein's equations, the size that defines how close you are to the point of no return. So when scientists measure these echoes, they are probing regions where gravity bends light dramatically. Time slows relative to distant observers. Atomic particles move at a significant fraction of light speed. This is physics at its limit. And here's something even more exciting. The same techniques being used on stellar mass black holes may soon be applied to supermassive black holes in distant galaxies. If that works, we could map feeding zones around black holes millions or billions of times more massive than our Sun. We could watch galaxy-scale engines in action, all from tiny flickers of X-ray light. And sonification adds a human dimension to all of this. It bridges the gap between abstract numbers and intuitive understanding. When you hear the rising pitch, you're hearing energy increase. When you hear rhythmic pulses, you're hearing structure. When you hear chaotic shifts, you're hearing instability near the edge of spacetime itself. It turns invisible physics into something almost tangible. So no, we're not hearing air vibrate in space. We're hearing data. We're hearing gravity translated. We're hearing matter at the brink of oblivion. And the more we refine these techniques, the clearer that voice becomes. Black holes were once thought to be simple, just mass and gravity. Now we know they are dynamic systems. They breathe in matter. They flare. They shrink and expand. They launch jets across light years. And thanks to reverberation mapping and sonification, we are no longer just watching them. We're listening. And the universe, it turns out, has a lot to say.